Sampling distributions, section 5.4. We've talked about the relationship between the mean of a population and then the values of a random variable. Do you remember that? Good. Today we're going to talk about the relationship between a population mean and the means of the sample taken from that population. Okay? So first of all, definition of a sampling distribution. Okay? Yeah, the section's called sampling distributions, but if you don't know what it means, it doesn't help at all. Okay? Definition. The probability distribution of a sample statistic that is found when samples of size n are repeatedly taken from a population. Okay, so we're going to take a whole bunch of different samples from a population. We're going to make sure all those samples are the same size, and we're going to find the mean of each one of those. Sorry, I haven't told you that yet. We're just talking about the probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from the population. Okay, I got ahead of myself, excuse me. So first of all, if the sample statistic is the sample mean, then the distribution of the sample distribution, let me say that again. If the sample statistic is the sample mean, then the distribution is the sampling distribution of sample means. Okay, it's a lot of saying the words distribution and a lot of saying sample means, but give me a second and we'll get through this. Okay, every sample statistic has a sampling distribution. Let me just draw you a picture. How is that? Will that work? Here is a population. You guys know Venn diagrams pretty well, don't you? Thank you. So here's a Venn diagram. Here's a population. This population has a mean and it has a standard deviation. I'm telling you that up front. Okay? Let's say I'm going to take a sample size n. Not very good at that. We're going to call this sample 1. Does it make sense that this would be the mean of that sample? Do you remember that this is how we denote the mean of a sample by using x bar? Okay? So that's the mean of sample 1. How big is it? How many items are in the sample? N, right? We don't know, so we call it n. Okay? Now let's take another sample from this sample distribution, or from this population, excuse me. What's it going to be called? Sample 2. And how would we denote this for it? X bar 2, right? X bar sub 2. What if, oh, and how big is it? N, okay? What if in the next sample that I took, some of the same information that was in the sample that I just took is in the new sample? Is that okay? As long as it's the same size, right? We're really focusing on making sure our samples are all the same size. So we're making sure it's sample size n. This one is called sample 3. X bar 3 is the mean, right? Am I then allowed to take another sample and that could contain information both from sample 2 and sample 3? Is that allowed? Yes. It would be called sample 4, and the mean would be x bar 4. That's how we would denote it. Can I take one more sample? Can I take 17 more samples? Yes, right? If I take one more sample, it might be over here. It might be some of the information we haven't taken yet in any of the other samples, but it's still part of the population. This is sample 5. And its mean would be called x bar 5. Okay? So here's some things you need to know about this sampling distribution. What do you need to know? Properties of this sampling distribution of sample means. Now do you see what I'm talking about? I have a sample means. See, right now I have 5 sample means. Does that make more sense when I talk about sample means? So this is a sampling distribution of sample means. You know when you say a word so many times it suddenly doesn't make any sense? That's where I'm with sample right now, just so you know. Okay? Okay, so first of all, the first property that I want you to know of is this. The mean of the sample means, which we would denote as the mean of the sample means, is equal to the population mean. In math, right, we would write that like this. The mean of the sample means, if I added all these up and divided by 5, the mean of the sample means is equal to the population mean. That is a property of sampling distributions of sample means. You okay with that? This is going to come into play on quite a few of your homework assignments as well, so you got to keep that in mind. Okay? Also, if you know the population mean, don't you also know the mean of the sample means? Okay, good. Okay, so property number 2. Can we make this agreement? If I write this, what does that mean? Can we make it mean standard deviation? Here, I'll write it on the side. Standard deviation. D-E-V-I-A-T. Okay, that's not any like accepted abbreviation. That's me not wanting to write standard deviation a lot today. Are you okay with that? Great. The standard deviation of the sample means, and we denote that by this, like that, is equal to the population standard deviation, that we call that, divided by the square root of the sample size. And we've been calling that sample size n. Okay? So in math, we would write it like this. The standard deviation of the sample means equals the standard deviation of the population divided by the square root of the number of terms, the sample size. Okay? The standard deviation of the sampling distribution is called the standard error of the mean. Everybody okay so far? You got this? Okay. I've got 4 slips of paper. That's what I wrote on each of the slips of paper. Okay? One has a 1, one has a 3, one has a 5, and one has a 7. I'm going to fold these slips of paper up and put them in a box. Shake up the box. I'm going to pick one, write down what it says, I'm going to put it back. I'm going to pick another one. Write down what it says. Okay? So I need to know first of all, list all possible samples of size n. Well, what did I say? How many times am I going to draw? 2, right? So my sample size is going to be 2 in this problem. So if I'm going to list all possible sample sizes, what's the first possible thing that I could draw? Well, I could draw a 1 and then a 1, right? Because I put it back. Mathematically, that's called with replacement. I draw with replacement. Okay, it means I'm going to draw and put it back before I draw again. Okay, what's another sample that I could draw? 1 and 3. What's another one? 1 and 5, and then 1 and 7, right? Is that the only ones that I could draw? Okay, then what else could I draw? 3 and 1? How about 3 and 3? And then 3 and 5? I could have put 3 and 3 right there, but kind of want to keep stuff like in an orderly manner so I don't forget anything, right? And 3 and 7? What else could I draw? What you got? Oh, we're not talking about that yet, but yes, that's a good question. Okay? But if order matters, then yes, they are two completely different things. If order doesn't matter, then they are the same. Okay? Sometimes order matters and sometimes it doesn't. We're not quite there yet. Okay? So I could do a 5 and a 1, a 5 and a 3, a 5 and a 5, and a 5 and a 7. And then I could do 7 and 1, 7 and 3, 7 and 5, 7 and 7. You got that okay? Yes? Okay. So what is my sample size? 2, right? I have 2 choices to come out of here. How many possible samples do I have? 16. So I have 16 possibilities. I got to keep that in mind, okay? The first thing I want to find for each one of these samples is I want to find the mean of the 2 numbers that I drew. Would that be a hard task to perform? Well, what's 1 plus 1? 2. 1 plus 1 is 2. And then I divide it by my sample size, which is 2, and I get 1. Right? Then 1 plus 3 is 4. Divided by 2 is 2. Can you finish this out while I finish it out? Don't look at mine. You can refer back up to it and make sure, but go ahead and go through yours while I go through mine. And then check. Okay, are your means the same as mine? Do we get the same means? The next thing that it asks us to do in this problem is to create a probability distribution of the sample means. Okay, so here's how I'm going to start that. Here's the B-R-O-B-A, probability distribution of the sample means. Well, the mean on my list of means, I got a 1, a 2, a 3, a 4, a 5, a 6, and a 7. Is that what you got as your means? And let's figure out the frequency of each one of those. How many times did I get a 1? How many times did I get a 2? 1, 2. Okay, how many times did I get a 3? 1, 2, 3. How many times did I get a 4? 1, 2, 3, 4. What about a 5? 1, 2, 3. And a 6? And a 7. Okay. Now let's find the probability of each of these frequencies. Okay. Well, it happened 1 out of how many times? 16. Now I know you know these decimals just right off the top of your head, so I'm just going to go ahead and write them for you if that's okay. Okay. How many times did a 2 occur? How many? 2 out of 16. Can we go ahead and leave them all out of 16? I know that that simplifies. I'm not disagreeing with you that that's 1/8, because it is. But let's leave them all as 16 so we can make sure that our math holds up at the end. Okay? So 0.125. What about, how many times did we get a 3? 3 out of 16. How many times did we get a 4? 4 out of 16. Whoops. How many times did we get a 5? 3 out of 16. How many times did we get a 6? And how many times did we get a 7? Guys, what should our frequency numbers right here add up to equal? Our frequency should add to 16, right? That's how many times, how many samples I have, right? What should our probabilities all add up to? That's the 1, right? All the probabilities should add up to 1, because these are the only possibilities of our distribution, our samples that we took. Okay. So watch this. I want you to see what this looks like. What did I just make? Do what? Starts with an S. Symmetric, right? But what is this thing actually called? You remember? It is a histogram, okay? So this is a probability histogram of my sampling distribution. Of my sampling means. Now, what you saw right away was the significance of this, okay? The significance of this is that it's symmetric. Would you say it's almost bell-shaped? Like if I drew a bell shape on the top of it, would it fit for that? Okay? Because it's similar to a normal curve, we're going to talk about that in just a second, but this is what I want you to keep in mind when we're talking about the normal curve. Okay? I might refer back to this if I can remember. Okay? Based on previous formulas that we know, and because of things that we can figure out ourselves, we can figure out or know that the mean of the samples is 4. If we add these all up and divide it by 16, we get a 4. That is the mean of the sample means. Using our formula for variance, we could find out the variance of the sample means. And using our formula for standard deviation, we could find the standard deviation of the sample means. Dang, I forgot to abbreviate it. Gosh. Okay, so far? Okay. The central limit theorem is a huge deal in 5.4. Okay? On page 263. Oh my gosh, that is so funny. I opened my book up one page away from where I need it to be. That's so cool. Okay, on page 263 in your book, if you want to refer back to that, go and write the page down. Okay? So you can either look in your book if you have a book, or you can look online at the textbook online. It's on page 263. Okay, is where the central limit theorem is. But before we talk about like what it actually is defined to be, I want to tell you about the central limit theorem real quick. Okay, first of all, it forms the foundation for inferential branch of statistics, not brand, branch. Okay, where we can infer things. We're not just assuming things, we're taking mathematical knowledge and we're figuring stuff out by inferring it. Okay, this theorem also describes the relationship between the sampling distribution of sample means and the population that those samples are taken from. Okay. There is a relationship, and this theorem describes that relationship, the central limit theorem. Okay? It's also an important tool that provides the info that you will need to use sample statistics to make inferences about a population mean. All right? So, number one, this is the first part of the central limit theorem. Okay? And like I said, you don't have to write this down unless you just want to. It is on page 263 of your book. You can look it up. Okay? So first of all, if samples of size n, where n is greater than or equal to 30, are drawn from any population with a mean and a standard deviation, then the sampling distribution of sample means approximates a normal distribution. The greater the sample size, the better the approximation. Okay? Let me give you a visual representation of what I am talking about. If I give you any, whoa, you can't even see that. If I give you any population distribution, and I tell you the standard deviation, and I tell you the mean, and I start taking sample sizes from this population distribution, and I take my sample sizes to be greater than or equal to 30 things out of that population distribution, the sample is going to end up looking like this. Your mean is the highest one, your standard deviation is over here. And you find that by taking the standard deviation of the population and dividing it by the square root of that number, of the number of terms that you chose, which is going to be greater than or equal to 30. Now, is that a big deal? Huge. What have we done before that has this shape? The standard normal distribution, right? So what's cool about the standard normal distribution is that we have helpers for that, right? If it's not a standard normal distribution, can we use these charts? No. Okay, but if we can get it into a standard normal distribution, we can use these charts to help us find area, to find probability, all sorts of things, right? So that's a good thing. But here's the really cool deal. If the population that you choose is already normal, if it's already normal, it doesn't matter what sample size you take. It could be any sample size, any number, and the sample is also going to be standard normal distribution. That's pretty cool because once again, I can use my tables. Okay? Is there any point in time where I would need to use my tables? Well, of course, or why would we even be talking about it, right? The probability and central limit theorem is right here. Let me zoom in so you can see a little bit better. In section 5.2, you learned how to find the probability that a random variable x will lie in a given interval of population values. In the same way, or in a similar manner, you can find the probability that a sample mean x bar will lie in a given interval of the x bar sampling distribution. To transfer an x bar score to a z-score, you can use this formula. And they give it to you. Okay? Value minus mean divided by the standard error. So the mean x bar minus the mean of the x bars divided by the standard deviation of the x bars, also called the standard error. Okay? And just in case you need to know, that's on page 266 in your textbook to refer back to. Okay? Cell phone bill for the residents of a city have a mean of $47 and a standard deviation of $9. Random samples of 100 cell phone bills are drawn from the population, and the mean of each sample is determined. Find the mean and standard deviation of the sampling distribution of sample means. If you know that the mean of the population is 47, what's the mean of the sample means? Do you remember what we talked about before? The mean of the sample means is equal to the mean of the population. So if you know the mean of the population is 47, then that's also the mean of the sample means. Remember how I told you that that would be important to refer back to? Well, like right now. Okay? Then it says find the standard deviation of the sample distribution. Well, we have a formula for that. We're not trying to guess. We're not trying to figure it out. We can plug everything into the formula that we know. The standard deviation of the sample means is going to be the standard deviation of the population divided by the square root of the number of terms or the number of samples that you took. Okay? 9, it told us that in the very beginning. It has a standard deviation of $9. So 9 divided by the square root of 100. Where'd they get 100? Random samples were taken, 100 random samples. So that's where it is. You know that the square root of 100 is 10, so 9 divided by 10 is 9/10. That is the standard deviation of the sample means. Any questions about that? Okay. Assume the training heart rates of 20-year-old athletes are normally distributed, with a mean of 135 beats per minute and a standard deviation of 18 beats per minute as shown in the figure right here. Okay? Random samples of size 4 are drawn from this population. Why is it okay to take a sample of size 4 from this population? I thought it said it had to be over 30. This one we just did was 100. Why did this one have to be 100 and this one can be 4? Yes, it is. That's very good. This one's already normally distributed. Can you tell that this one's not? I mean, it's close, but it looks like a mountain, but more than a bell curve, right? Okay. This one looks like a bell curve. It's already normally distributed, or standard normal distribution. Okay. But I can have any sample size because it's already that way. Okay, so find the mean. If we know the mean of the population, do we know the mean of the sample size? 135. Okay, and then once again it's asking us to use that same formula for the standard deviation of the means by taking the standard deviation and dividing it by the square root of the number that you chose, the number of samples. Everybody understand? Okay. Look at number 4 then. Example number 4 is based on the fact that we're trying to find a probability and use the central limit theorem at the same time. Okay? The figure at the right shows the lengths of time people spend driving each day. Isn't that an adorable chart over here with these really cool red cars? I was just teasing. Okay. You randomly select 50 drivers ages 15 to 19. What's the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Are we okay with this? Do we know that this is a standard deviation kind of deal, a standard normal curve? Can't really tell from how it's written, right? So we need to make sure that our sample is more than 30, which it is. We've got 50. We're okay. Okay, so the sample size is greater than 30, so you can use the central limit theorem to conclude that the distribution of sample means is approximately normal. Since we're choosing more than 30, we can just go ahead and say that. We can infer that with a mean and a standard deviation of, why can we assume this one as 25? Any idea? Anybody? Maybe we can think about it for a second. The mean of the samples should be the mean of the population, right? What sample are they asking us for? 15 to 19? What's the mean of 15 to 19? 25. Do you see where they got 25 being the mean? You okay with that now? Okay. This is the standard deviation of the means. We take the standard deviation, divide it by the square root of the number of terms, 1.5 divided by the square root of 50. Why can we say that the standard deviation is 1.5? Yeah, it tells us that right here. Okay. Well, what do I do with that? We want to use that formula that they gave us that you can't see it now. This one right here. Don't we know all these things? We're just plugging things into a formula now. It's something you guys are really good at. The hardest part is figuring out what goes where, right? What stands for what. So 24.7 is the starting one that we want to look at. Okay. Minus the 25 divided by the 1.5 divided by that thing we just found. Okay. That gives us negative 1.41. Now we want to convert that to a z-score. Or sorry, that converts it to a z-score, right? So, same thing here. Why are we doing it twice? It wants a range, right? So we got to go to the outer ridges of that range. So, if we're trying to find the probability that it's here, we just use our z-score numbers. That's the z-score for the 2.36. That's the z-score for the negative 1.41. That's the z-score for the 2.36. And we just subtract them because we're trying to find the area in between them. Remember that? Again, that's stuff we've already done. Okay, we're just starting to put it all together into one lesson. All right? Any questions about any of that? Anybody? Okay, so that's 5.4.